In this video, we will talk about the first of the three great vector calc theorems, and that would be Green's theorem. The main ideas of this video is all captured in this one slide. After this slide, we will go into three examples, two of which has a great deal of detail about Green's theorem. Then there's the third example, and then there are three problems for review for you to try. I do sometimes refer to this summary sheet that I had covered in a previous video. Often I have this sheet somewhere in a corner, so it's very small, but if you would like to refer to this as well, maybe you can screenshot it so you can look at the full size as we go. We start with the statement of Green's theorem that says if D is a region of type 3 and C is its boundary, then suppose that we have P and Q and their functions from our domain to R1 and they're of class C1. Then the integral over the boundary C of P dx plus Q dy is equal to the double integral over the volume of the area of D, derivative of Q with respect to x minus derivative of p with respect to y. I kind of find the p's and q's distracting, so I like to think of this as a vector field f of x, y, where the function that maps to the x-coordinate is considered to be p, and the function that maps to the y-coordinate is considered to be q. And what Green's theorem does is it relates a line integral around the boundary of a region. So here we have a region D, and we can do a line integral around the boundary, and it relates that to an area integral over the interior of the region. So we can do an integral over the boundary, or we can integrate over the entire area with a double integral. And the double integral is something that we had done a couple of chapters ago. So Green's theorem allows you to convert back and forth from a line integral to a double integral. Because we are doing a line integral of a vector field, we are on this part of our chart, and I have copied the formula or the equation for the line integral over here for your reference. So Green's theorem applies to any decent region in R3. So for example, the annulus can be broken up into 4 different regions. And also these curves, these bounded curves, do have orientation. And the positive direction is in the counterclockwise direction. Or you can remember, if you walk along the path in the positive orientation, then the curve D, or the area D, will be on your left. And remember, what Green's theorem tells us is we could take this integral along the path here that I'm highlighting in yellow, or we could take the double integral over the domain, which is the area I am highlighting in green. Now is a good time for an example. So we're going to verify Green's theorem when p of xy is equal to x and q of xy is equal to xy, where d is the unit disk. And then I also wrote this in terms of f of xy in the way that I like to see it, which is x and then xy. Also, a quick note, the reason why the problem talks about a unit disk is because a circle, if you recall, are the points that are equidistant from a center point. So the circle actually is only this outside here, the boundary. If you want to talk about the interior of the circle as well, you have to talk about a disk. So to verify Green's theorem, I'm going to start by calculating this on the left-hand side, which is the line integral. So the line integral of p dx plus q dy, so in other words, of x dx plus xy dy. If you are following along on our chart, we have a vector field, so we're in this column, and we are doing a line integral, so we're in this row. So this is where we're at right here. We're using this formula here in these 4 steps. And if you recall, the first step in doing these line integrals is to parameterize our path. And in this case, our path is the circle. Again, it's the boundary, the circle of radius 1. So in this case, our radius is fixed at 1. We don't want to go from 0 to 1 because we don't want the interior. We only want the radius of 1. So we have 1 cosine theta, 1 sine theta, and theta goes between 0 and 2 pi. Next, we compose our f of sigma of t. So then we plug in f, we have our cosine theta, sine theta, and then we need to find our function f, which is equal to x, which is cosine theta, x times y, which is cosine theta sine theta. The next step is to take the derivative of our sigma, so we have negative sine theta, cosine theta, and then we're ready to plug in our integral. So our limits of integration are here, 0 to 2 pi, and then we put our f composed of theta, cosine sine theta, and then we dot that with sigma prime of t, which is minus sine of t cosine of theta. And the rest is integrating and plugging in. Next, we're going to do this same problem, except with the right-hand side. We're going to do the integral over the entire area of the circle. In this case, we're looking at a double integral over the circle here as our domain. Because it's a circle, I have chosen to use polar coordinates. And when I use polar coordinates, I will need to use the Jacobian, because here I have things in the rectangular coordinates, so I will need a change of coordinate systems. Here are my polar coordinates, and then I calculated my Jacobian is equal to r, and I reminded you what that calculation is. What you do is you go to your x equation, and you take the derivative with respect to theta, and then you take the derivative with respect to r. You do the same for y, derivative with respect to theta, derivative with respect to r, and then you do the determinant, which is negative r, but the Jacobian is always positive, so you take the absolute value and you get r. Okay, so I'm just about ready to plug in, but because dq dx, that's the partial derivative with respect to x of q. Where is q? Q is here, xy. That would be y. The partial derivative of p, which is over here, with respect to y is equal to 0. So then what I have is the derivative over the domain of y, because I have 0 here, dy dx. As I mentioned, I wanted to do this in polar coordinates, so my r goes from 0 to 1, theta goes from 0 to 2 pi, I have my Jacobian here, r, and finally I have my y, which is just r sine theta. Oh, so r sine theta here, here's my Jacobian r. And then after that, it's just integrating and plugging in. And you see that I have the same answer on both sides, doing it both ways. The last point I have with Green's theorem is there is this kind of a vector form that uses the curl. If you have f here written as a vector field, you take the curl of f, you dot that with k, and then you do your double integral. You can also write it using this notation for curl. And just to review what this looks like on our chart, Green's theorem, again, it had a double integral of the curl, and it related it to a line integral of a vector field over here. Another detailed example doing this integral both ways on the left and right for Green's theorem. So we're going to let f equal to the field xy squared, x plus y, and we're going to integrate the curl dot k in the first quadrant bound by the curves y equals x squared and y equals x. The first thing I do is I draw my curves just so I get a feel for what it is I'm integrating over. And since we are going to be doing a line integral of a vector field, I am over here on my chart and I write down my formula so that it's available when I need to use it. The first thing I want to do is parameterize my curve, and I'm going to break the curve up into two parts. The first one I'm going to do along the line x equals y. But as you can see, this is a closed curve, and the direction I'm going to parameterize it is in this direction here, from t going from 0 to 1, because that's what's natural to me. But because the curve is actually in the opposite direction, I'm going to need to remember to multiply my answer by -1. And when you have a curve with the equation y equals x, it's easy to parameterize. You just let t equal to x. So t can go from 0 to 1, x will go from 0 to 1. And then you write y in terms of x. In this case, they're equal. So y is also equal to t. So again, t goes from 0 to 1. So you can see from this parameterization, when t is equal to 0, our curve is at 0, 0. When t is equal to 1, our curve is at 1, 1. And when t is equal to 1/2, you get all the points in between. Our next step then is to write our field composed with our curve. I then take the derivative of our path, and then I'm ready to plug into our integral, and then the rest is integrating and plugging in. And I did put my negative sign because, again, I had parameterized going from 0 to 1 in this direction, but my curve is actually in the opposite direction. So here's my negative answer. Next, I'm going to parameterize the path along the curve y equals x squared. So again, because I have a function of y of x, I can plug in t for x and then just write y in terms of x, which is t squared. I kind of went ahead and did the next 3 steps. So I plugged in f composed of my curve, t. I took my derivative of t, and then I took the dot product and plugged everything into my integral and evaluated the integral. So for my entire path along this closed surface, I have my minus 5/4 plus my 4/3, which is minus 1/12. As I mentioned, I can now do this problem using the right-hand side of the equation. Or actually, I'm going to use the curl just to do something different now. I'm going to use the curl side of the equation. And the curl side of the equation is like the right-hand side of the equation since it's the integral over the area. So I'm going to do the integral over the area, over the entire area here of the cross product. So here I have done the cross product, and just to remind you, it's the del operator. The del is d dx, d dy, d dz, cross our vector f. And where was our vector f? Here is our vector f. And now I want to set up my double integral, and I'm going to set this up so that x goes from 0 to 1, and then y is going from this bottom curve, which is x squared, to the top curve, y equals x. And here is my integral. I have my curl dot k, and I set up my integral so that x goes from 0 to 1, and then y is going to go from the bottom curve x squared to the top curve x. When I do this dot product, because this is 0, it's only the k vector I want, so here is my integral. And the rest is just integrating and plugging in. But you will notice that I get the same answer as I did using the left-hand side of Green's equation. For my last example, I'm going to illustrate this point here, which is for any region D in the plane, you can get the area or half of the area by taking the line integral of this function. So this is a special function that allows you to do this. F of xy is equal to negative yx around the boundary of D. So according to this claim, if I wanted to find the area of this square, I could take the line integral around this square of this function, and I would get half the area of the square. We are going to test this out with a circle of radius r. So I look at my formula here. It says that 1/2 the line integral of this function, y, minus y dx, x dy, here, will give me 1/2 the area of my circle of radius r. My first step is to parameterize my curve, and I'm on the boundary of the curve. So I'm going to fix my radius at r, and I parameterize as r cosine theta, r sine theta. Theta goes between 0 and 2 pi. And again, it's important to realize that r does not go between 0 and 1 because I don't want the interior of the circle or disk. I only want the boundary, which is why I have r fixed at the radius r. Next, I compose my f with my curve. I take the derivative of my curve, and then I can plug in to my integral. And the rest is calculation, and you'll see I get 2 pi r squared. And according to this formula over here, the area of my circle should be equal to 1/2 of my line integral, so that would be pi r squared. I just realized I started out by drawing a square and saying we were going to find the area of a square, but then I parameterized a circle. So here it is. This is the area of a circle. Sorry about that. Oh, actually, that was my instructions here. I don't know why I drew that square, but ignore it. So that wraps up the examples. So on the next screen, I'll have some problems for you to try. You can pause the video, and then on the next screen when you come back, I'll have solutions for you. Here is the first solution done as both the double integral of it over an area as well as the line integral. This is the second solution. I used the formula in the vector field we had in one of our examples. And this is the last solution, again done both as a double integral over an area and as a line integral. That's it for this video. Thank you for watching.